matrix material, and it depends on what type of material you are using. You can use either metal, polymer, or ceramic. And then second phase is the reinforcement, which can be used in the metal matrix material. Then you have the interface between the matrix and reinforcement. So so we have three types of classifications in the composite materials. We have particle reinforced composites, whisker or short fiber reinforced composites, and then we have continuous fiber reinforced composites. Okay. So, but today I will be discussing about the particle reinforced composites. When we talk about the composite materials have various applications in the automotives and then aerospace applications. And then because these composite materials have high strength and lightweight, they have improved stiffness, as well as they can operate at the maximum temperature. When we talk about the market of the composite materials, you can see from this slide that the green zone is the highly demanding zone where the composites are being used. So India is one of the leading country. You can see the composite materials are being used in various sectors. And then when we talk about the publications in the area of composite materials, India is leading. India is publishing many papers significantly higher compared to the other countries. Okay. Now, let me give you the brief idea about the different processing techniques for making the MMCs. So we have three types of processing. One is vapor deposition, liquid state processing, and then solid state processing. So in the vapor deposition, we have CVD, PVD techniques, but they are expensive and they have limitations. They cannot be used for the mass scale applications or bigger size applications. And then we have the liquid state processing, where we have stir casting, gas pressure infiltration, squeeze casting, infiltration techniques. Okay, so these are the cheap methods and they can be used for various applications at the mass scale. And then we have the solid state processing. Okay, and so today I will be talking about the friction stir processing. This is one of the thermomechanical solid state processing techniques, and it is based on the friction stir welding. Okay, so composite materials are developed by different techniques. When you manufacture these composite materials, then you have to study about the different strengthening mechanisms. How can you improve the mechanical properties? So we have the four strengthening mechanisms in metal matrix nanocomposites. So we have grain refinement strengthening, that is called the Hall page strengthening. Most of you will be aware of this equation. And then we have the Orobon strengthening, where the dislocation multiplies. And then we have the coefficient of thermal expansion mismatch between the matrix material and the reinforcement. And then we have the load transfer strengthening mechanisms. So these are the four basic strengthening mechanisms, and I will give you some of these examples from the whatever composite materials we have developed. So another thing is, as I discussed in the solid state processing, we have powder metallurgy technique. So this is the powder metallurgy schematic. Okay, we do the milling process for the powder material, and we use different type of millings, ball millings. So we have planetary ball milling, iterator milling, specs milling, and cryo milling. Okay, so we use different type of medium in these milling process. And after the milling of the powder, we get the fine size powder, and then we use the cold compaction or hot compaction process to get the final shape. Okay, so now we have understood that the metal matrix composite materials have high strength to weight ratio, they have high thermal conductivity, and low coefficient of thermal expansion, they have high wear resistance. But the controlling parameters for these composite materials are dispersoid, means reinforcement, their size, shape, content, and distribution. These all factors will affect the performance of the composite materials. and then we have the interface between the matrix and the reinforcement, and then we have to design the microstructure, and then we have to find out the properties. But the challenge is reproducibility, uniform distribution of the fine second phase particles, and then sound interface. Okay, this is the main challenge. Okay, so we are trying to address this challenge using the friction stir processing. Okay, so most of the composite materials will have the high strength but low ductility and less toughness. So we are trying to address this issue using the friction stir processing method to develop these MMNC. So conventional methods are mechanical alloying and solidification processing, but we have limitations as I mentioned, the poor bonding between the interface and poor wettability, the agglomeration of the second phase particles, porosities, and then the material cost. So these all can be addressed using the friction stir processing method. When you develop the metal matrix composite materials using the liquid route or casting method, then you have the following issues: transfer of reinforcement into the melts, movements of reinforcement into the melts, effect of reinforcements on viscosity and fluidity of melts, and then effect of reinforcement on nucleation, growth, and microsegregation. And then we have the effect of distribution, bonding, volume fraction uh, on physical and mechanical properties of the cast MMCs. So these are the issues when you use the liquid route or any casting process to make the composite materials. So here I will be talking about the friction stir processing. So this is the schematic of the friction stir processing technique. This is based on the friction stir welding. So here we have the friction stir welding tool, and this tool rotates at high RPM depending on the material, and this tool will be inserted inside the material, and then when this shoulder will touch to the material surface, there will be a friction between the material and the tool shoulder, and due to that friction material will plasticize and the processing will take place. Okay, so the difference between the FSW and FSP: in FSW you have the two metallic plates, but in FSP you can use only single metallic plate to refine the grain size and as well as the refine the microstructure and remove the defects. So once you complete this process, you have the four types of zone. In the center of this processing zone, you have the stir zone. This is called the stir zone. And beside this stir zone, you have the thermomechanically affected zone. And beside this thermomechanically affected zone, you have the heat affected zone. And this is the base material. Okay. So when we use this process to make the composite materials, most of the time you get the composite materials in this zone, stir zone. So whenever we will talk about the FSP composite, we will talk about the stir zone. Okay, but the challenges are wearing of the FSW tool. Okay, so with this tool which is used in this process gets weird when you use this process for making the composite materials, because in the composite materials you use ceramic particles as second phase material. Okay, and those ceramic particles are very hard. Okay, so due to that you can see it is reported that this materials, you can see the geometry of the tool, FSW tool, is getting changed. Okay, this material is getting worn out and then it is going to be mixed in the material matrix material, so the properties will change. So whatever you design, that you will not get if it is, if this issues is there. Okay, so you have to rectify this issue. And how will you rectify? So we have followed the polymer derived ceramics approach. What we have done is we have used the metal matrix material, and then we have used the cross-linked polymer powder as the reinforcement. So this cross-linked polymer has the special property that this powder can change into the ceramic phase uh, under the certain temperature conditions. Okay, so this cross-linked polymer can change into the ceramic phase around 800 to 1000 degrees Celsius, and then what will happen, due to the phase change there will be evolution of some gases, and those gases will produce some voids, and those voids you can remove by further multi-pass FSP process, and then the ceramic phase particles can be redistributed in the metal matrix in the nanoscale. Okay, so that is the whole concept which we have used. So polymer derived ceramics are the materials formed by the pyrolysis of the pre-ceramic polymers. So we have the two categories. One is the silicon carbonitride. These are the one type of PDCs, and this is silicon oxynitride. This is another type of PDC. So these two type of PDCs are used, and they have a special property. They have polymer to ceramic transformation around 800 to 1000 degrees Celsius. So this property you can use, you can utilize as reinforcement in the metal matrix. So people have used this polymer material, PDC material, using the casting process as well as the powder metallurgy process, but they did not solve the problem of the agglomeration. They did not get the nano size distribution. Uh, okay, so we have used the FSC process. So this is the schematic of the sample production. Okay, so this is the basic, very preliminary schematic. You can see, you can design your own sample as per requirement. But this was the beginning idea. How can we insert the polymer? So this is the metallic plate, and we drill the hole and the groove on the metallic plate, and we fill the powder, and we covered with the small thickness plate. Okay, then this is the 5-axis twistor welding machine, and this is the FSW tool. So we optimize the process parameters. So we did the 4 multi-pass FSP process, and the tool RPM was 1500, traverse speed was 25 per minute, and then tool tilt angle was 3 degree. So you can see this is the processed FSP of processed matrix material copper. So we use the copper as a matrix material, and then silicon carbonitride as the reinforcement material. So you can see this is the picture of the processed copper SiCN composite sample. Now let us discuss about the microstructure. So this is the microstructure of the copper, anneal copper material, around 400 micron size grains you can see. And then this is the as received silicon carbonated polymer particle size of around 5 micron. And then we mix this polymer powder in the metal matrix, and we did the multi-pass processing, and we have seen after the each pass the size of this polymer powder was getting reduced, and it went to the nano size. Okay, so what will happen after this mixing? We do the pyrolysis. Pyrolysis around 800 to 1000 Celsius. Even during the process also, the temperature will reach around 800 degrees Celsius, and due to that, the pyrolysis process will take place, and due to that pyrolysis, the evaluation of gases will happen, and they will produce voids in the ceramic particles. So these voids can be reduced further by using the multi-pass FSC process. You can do further FSP process on this material, and then you will get the fine distribution of the ceramic particles. Okay, so this is the SEM pictures of the at different passes, okay, of the ceramic phase particles. This is the proof where we can see the distribution of the ceramic phase in the metal matrix. So we have the silicon carbonitride, all the particles are nicely dispersed in the matrix, and then we have analyzed how this ceramic particles are getting fractured during the process. So in the FSP process, we have the frictionister welding tool, and that tool rotates at high RPM. So due to that rotation, there will be a shearing force on the particles, and due to that shearing, this particle will keep on fracturing until it reaches to the nano size. Okay, and then we also find out that how much temperature is there during the process. So you can see here the temperature raised around 700 or 800 degrees Celsius. Okay, this temperature is sufficient for the pyrolysis process. So at this temperature, the silicon carbonitride polymer, cross-linked polymer, will change into the ceramic phase. So these are the ceramic phase, silicon nitride and silicon carbide. These are the two ceramic phases we recognized in the composite material. So this process also can be used for getting the for making the metallic foam, okay, because as I mentioned that during the pyrolysis process these pores or voids will be developed in the inside the material. So you can use this material as the metallic foam for different applications, for energy absorption applications or shock absorption applications. Okay, now let us discuss about the uh, strengthening mechanisms and the grain size. So as I mentioned that we use the annealed copper, okay. So the grain size in the annealed copper was around 100 micron and it gets reduced to the 2 and 2 micron, okay. So you can see the EBSD pictures of these grains, and then in the left side you can see the transmission electron microscopic analysis. So you can see the 20 to 30 nanometer particles are dispersed inside the matrix material, and this is the interface between the particle and matrix. You can see there is no defect at the interface. This interface is sound interface, and as I mentioned that these strengthening mechanisms about the metal matrix composite materials, we have the dislocations, tangle dislocations, pinning by grain bound dislocations are pinned by the ceramic particles, and as well as we have the grain refinement. So this will contribute to strength the to increase the strength of the uh, composite materials. So the interesting result is, as I mentioned, that most of the composites developed by the conventional process, for example, metal casting, they will have the high strength, but they will have the low fracture toughness. They will have the less ductility. But in our case, we have achieved a high strength and high ductility composite. We have not compromised ductility. So this is very important to increase the fracture toughness of the composite materials. So this is very unique result using this process. This is the unique finding. And then we have done the tool analysis, geometric analysis, and we have found out that there is no uh, wear in the tool, okay, or you can see there is no change in the geometry of the tool. So we have saved the tool life. This tool was traveled around 1.4 meter, but we have not seen any wear on the tool, okay, and you can see the geometry is retained. So this is the important thing which we have contributed to save the tool life as well as to increase the strength as well as ductility of the composite materials. Second example is aluminum TiO2 nanocomposite. Similarly, we have developed this composite also. You can see 6 multi passes we have done. So you can see this is the final uh, sample of aluminum TiO2 nanocomposites. You can see this TiO2 composite, TiO2 materials, ceramic particles are distributed in the aluminum matrix, and you can see again this is the mechanism how this particles is getting fractured after each pass. So you can see this particle will have the pores, and this pores will have the less fracture toughness, okay. So when you do the multi-pass process, these particles will keep on fracturing until they will have the nano size range, okay. So this will be distributed in the aluminum matrix. So here also we have achieved the high strength as well as the high ductility of the composite sample, okay. So these are the very real examples of developing the metal matrix nanocomposite materials using the FSP process, and we have compared the results, experimental results, with the theoretical models, and we have seen that it is comparable. The results are matching. Now we have the so we have again find out the strengthening mechanisms. Uh, uh, Similar strength, you can see the multiple dislocations are here in the composite materials, and these dislocations are pinned by the ceramic particles, okay. Now another recent development we have achieved is mixing the graphene nanoplatelets into the aluminum alloy composites. Okay, so what we have done here is we have tried to mix the graphene nanoplatelets inside the aluminum matrix, alloy matrix. So the approach was we use the squeeze casting process. Okay, we have used the squeeze casting to mm, deposit this GNP on the aluminum A356 alloy. So you can see in this SEM picture, this is deposition of the GNP, and then on this deposition of this GNP on the alloy, we did the FSP process. Okay, so what FSP process will do here is this FSP process will embed this GNP material inside the metal alloy. Okay, so this is the microstructure. You can see this is the processed zone, FSP process. You can see this is the ester zone here. So here you can take the microstructure. You can see these GNP particles are embedded in the metal matrix, material aluminum matrix. So this is the graphene nanoplatelets. You can see here, this is embedded in the material, and this is the interesting result which we got here. Again, you can see here, this is the A356 reinforced with GNP, and this is the base material. So you can see there is an increment in the strength as well as the ductility and toughness of the material. So I have given you three examples, real examples. How can you increase the mechanical properties, very crucial properties such as strength and toughness of the composite materials. Okay, and they are very crucial for different applications in automotives and aerospace. Okay, so this is the, if I summarize the work, a novel process developed which has resulted in zero tool wear using this FSP process, and we have developed the copper PDC composite, aluminum TiO2 composite, and A356 alloy reinforced with the um GNPs. Okay, so these are the components which we have developed. Now let us discuss about the different applications of the composite materials. So as I mentioned that these composite materials can be used in aerospace. So this slide will give you the brief idea where these composite materials can be used. So this is the example of aluminum graphite composite we are in Hubble telescope. Okay, this is the example of the F16. Okay, discontinuous and continuous MCs are being used in F16. Okay, then this is the example of automotive applications in different brake rotors. Okay, electronic applications also, some of these components are being used. Okay, and in cylinder bore also these components can use, and in crankshaft. Okay, so these are the some of the applications in automotives. This is very important slide. Most of you will be interested in this. So this slide will give you the information what are the companies in the world make the composite materials. Okay, so these are the names of the different companies which are making these MMCs for different applications. Okay, so if you are interested you can note down these names of companies. Okay, and then they are the specific system, composite system for specific applications. So for example, aluminum graphite system, composite system can be used for cylinder liners. Okay, and piston, connecting rod, and driving shaft, cylinder liner, brake rotor. Okay, and connecting rod. Okay, and these are the different manufacturers. Okay, so like Ferrari, Nissan, Dural, Honda, Toyota. So these are the different manufacturers who are making these composite materials by using the casting process. Okay, and this is again a simple example of different applications of the metal matrix composites in automotives. Okay, so suppose for example if you need the high wear resistance in the composite materials, you can use the silicon carbide, alumina, and graphite reinforced micro and nano MCs, and these are the applications: cylinder liners, pistons, camshafts, brake rotors. And if you need lightweight as well as the energy absorption, you can use the metallic foam. I have given example of how can you make the metallic foam using the FSP process. And you can also use the fly ash stenosphere low density ceramic micro balloon for making the metallic foam for different applications, crumple zones and batteries, okay, and the other different applications. Then if you need the high self cleaning, self lubricating and self healing, so these are the next generation composite materials. Okay, so self cleaning materials, they use the hydrophobic reinforcements, okay, uh, for different applications, water pumps, water jackets, okay. So there you need the hydrophobic property on the surface of the composite material, okay. And then we have the self lubricating composite. These composites are very useful in the automotives as well as the aerospace applications, cylinder liners, pistons, okay. So what you can do here is you can use the micro and nano graphite, MOS2, TiBu2, hexagonal boron nitride, and these are the different reinforcements you can use to get these self-lubricating properties in the composite materials. Then another one, we have the self-healing material. So self-healing materials can be used uh, to uh, to uh, to heal the fracture. If any crack is there in the inside the material where you have the difficult to access, it is fatigue prone or some critical components such as driving shafts, steering knuckles, connecting rods, okay. So here you can use the self-healing composite materials, and you can use shape memory alloy or hollow reinforcements filled with the low melting healing agents in the metal matrix. So what you can do here is you can get the partial uh, gain in the performance of the self-healing materials. Okay, so these are some of the examples of the next generation composites. So this is also again very important slide as far as we you are interested in the applications. Now let me give you the glimpses of the composite materials being developed in the uh, different laboratories in India. So we have, this is the example of the Make in India technology. So these composite materials are developed at Advanced Material Processing Research Laboratory CSIR Bhopal. So they are developing this aluminum silicon carbide composites for brake drums. Okay, so this is a example, and this is another example of developing the functionally graded aluminum matrix composite materials. You can see cylinder liners, brake rotors, pistons, and these materials are being developed in NIST Trivandrum. Okay, so there is CSIR lab Trivandrum. They are making these composite materials. So there is a huge demand of these composite materials, and there is a market of these materials and parts in India. Okay, so as I discussed, these next generation composite materials are self-lubricating composites. We have the self-healing composites, and then we have the self-healing composite materials. Okay, so I have already explained it, but briefly, if you consider the self-healing mechanisms in the self-healing composite materials, you have the precipitation mechanism, you can use the nano shape memory alloy material, you can use the eutectic based healing also. Okay, so there are different mechanisms to develop the self-healing composite materials. So if you are interested, you can go through this paper. This is the paper we published in 2018, and it has detailed information about the self-healing composite materials. Okay, this is the example, real example. So you can see here, this is they have used the shape memory wires inside the matrix material. So you can see there is a crack inside it, and after some time this crack is getting healed. Okay, so this is a small example how can you heal the crack, but There are some other examples and applications for developing these self-healing composite materials. Okay, so now I will close. I will stop here with small details about the research imperatives. So, if you are interested to carry out the research in the area of composite materials, so these are the different research imperatives which you can focus. Prevent the agglomeration and clustering of micro and nano sized reinforcement during synthesis and casting of metal materials composites. You have to reduce the cost of the MMC and reducing the difficulty in machining of the MMC. You have to develop the property data. Okay, this is missing. A lot of people are developing these composite materials on different composite systems, but there is a lack of the property data. So if we can develop the property data, then a lot of manual work can be reduced, and that can be referred to develop the advanced composite materials. Okay, then recycling also is required. Low cost filling castings with low embodied energy using waste, sand, and fly ash fillers. Okay, so these are the different research areas where in future there is demand of these to address. And with this, I thank you one and all. Now I will be happy to answer your questions.
Uh, thank you for that enlightening and very knowledgeable session, Dr. Ajay Kumar.
Yeah, thank you, sir. Yeah.
Thank you. We have some questions with us. Some participants have been asking questions. So there is Mr. Kaushik Nath who is asking. So, Mr. Kaushik, are you there?
Yeah, I see some of the questions in the chat box.
Yes.
Is there any chance of grain
Yeah, I'll directly
in
connect you,
boundary
Kaushik Nath.
mobility which might be different of high temperature applications of the nanocomposites? Secondly, can genre pinning be helpful? Okay, so when you talk about the high temperature applications of these composite materials, as we have not, it is again a topic of research. We have not done a study on high temperature of these composite materials, but yeah, certainly there will be a chance of grain boundary mobility. Okay, and sometime this generating also will be helpful. Okay, what are the criteria of selection of the materials for making composites? Should we go for metals or metal oxide? Which one is better? So when you talk about the selection of the materials, uh, first you have, if you are considering metal matrix nanocomposites, you have to consider metal as a matrix material, and then you can consider ceramic particles. They are nitride oxides. Okay, but certainly you have to consider second phase particles as a reinforcement, ceramic particles. So they can be oxide, they can be nitride. Okay, is it is graphene or graphene oxide? So this we have used as a graphene nanoplatelets. So they are only graphene. This was the multi-layer graphene. This was not graphene oxide. This was multi-layer graphene we used. It is like a chunk graphite. No, you get no. So from that it was derived. It was derived in the multi-layer graphenes. Then
Hello.
yes, Kaushik.
Yes,
Yes,
yes, sir. Sir, in some cases, graphene oxide, I have seen that it can also be used, because
Yeah,
in one of the,
in some cases you can use, but I am giving my example. In our case, we have received the graphite uh, powder, and then what we did is we tried to,
yes, from graphite to graphene oxide you have made. I mean
yeah,
graphene. Okay.
graphene. So it was
Yes,
the multi-layer graphene. It was not single layer, because it is very difficult to get single layer. And we had a thought that using the FSP process, in the FSP we have a lot of shearing, right?
yes.
So can this graphite can exfoliate into the single layer graphene or multi-layer graphene. So that was the concept, okay, which we used to develop these GNP composite. Okay.
Okay, okay.
And then you are asking this, how does actually self-healing take place,
Yeah, that you
mechanism?
have already mentioned. I know. I asked it
Yeah,
earlier. That you have
yeah.
mentioned in one slide.
Yeah. So if you are interested, we have written one paper in 2018. You can refer that. We have mentioned all the mechanisms there.
Okay,
Okay,
okay.
and that is very nice paper. We have, that was a review paper. So if you are interested, you can start working on that. That is, this is the now demanding area. Okay, a lot of research is required in this area for various crucial applications.
Okay.
Okay, yeah. Any other question?
Actually, Kaushik sir has one more question left. That is self-healing
Yeah. No,
mechanism.
that he has already answered, I think.
Okay, okay.
Uh,
Okay.
so I think I asked another question also. So he said that sir, microstructure you said, but why don't you call it nanostructure? Because all your material in the nano scale range. I think.
Right. But here we are using the metal matrix nano composites. Okay, so nano is
Okay.
coming there. You can also call it nano structure.
Yeah,
Okay,
that's why I'm. Yeah.
yeah. It depends on how do you pronunciate, how do you. So that is the economic issue. You can say nano structure also.
Okay, sir. Thank you.
Yeah,
Thank you. So it's a nice presentation.
yeah.
Very good.
Anything? Any other question?
So I think that's all from our participant side. So if
Okay.
they have any doubts or queries, we'll try to
Yeah,
connect it with you.
definitely. My email ID is there,
Yes.
so you can
So
definitely write to me, and I
sure,
will
sir.
be happy to
So we'll
discuss further.
forward your contact details to the
Yeah,
participants so that
definitely. Yeah,
they can come in contact with you.
yeah.
So
Okay.
thank you again, sir, for sharing such
Yeah,
valuable knowledge with our participants. I'm sure
yeah,
many of us are inspired to start the research, and if the research is ongoing, then surely benefit very greatly from that.
yeah.
Thanks again for joining us, sir.
Thank you so
And
much. Thank you so much. Yeah,
thank you, sir, Ajay, sir.
yeah.
And I request the participants, the third session of today's will be started at 2 o'clock. So please come and attend that session. So we'll be closing this session. And thank you, one and all. Thank you, Dr. Ajay, sir.
Thank you.
And thank you, all the participants. Thank you very much. Thank you.